So let's start the next seminar. Grazie. The speaker is Jessica Massetti from Rome 3. And the title of the talk is on the persistence of periodic Lagrangian tori for symplectic twist maps.
Okay, thank you for the invitation to this beautiful workshop. Okay, so today I'm going to talk about this joint collaboration with Marie-Claude Arnaud and Alfonso Sorrentino. Sorry for the ones who already listened to this, but hope that it will be interesting again. So the main light. No, I switch it on actually. It's green. Is it? No. Maybe this is better. Maybe. Okay. Okay. So the leitmotif of this talk came from, takes its origin of the problème général de la dynamique stated by Poincaré in his methods of the celestial mechanics. So since when the investigation of which of the properties of an integrable system break or persist in the passage to a completely integrable case to the non-integrable regime, developed into several theories, now well established and known as the KM theory, where, with its measure theoretic flavor consists in proving that there is a large set of Lagrangian tori which persists with a quasi-periodic motion on it, or further with the existence of much more complicated compact sets which are invariant by means of variational method as developed by Aubry and Mather and Magnier, and then further by Fatih and what goes now under the name of weak KM theory, or by the qualitative behavior of a ball of initial data and its exponential stability by the Nikoroshev theory. So, but what means integrability? Well, depending on the context, it can be characterized in different way. But so, for example, the Liouville-Arnold integrability with the existence of a maximal set of commuting integral of motions, or but that this is always also can be characterized, under some conditions on the level set of your energy level by the presence of an invariant foliation of the phase space, which can be either regular or allowing singularities, and that gave birth to further theory, localizing at the singular level, developed by Weil, Eliasson, and so on. But the main point is that integrable systems are pretty easy to break. And so, which means that in some sense, they are rigid. And in this talk, let's say the point of view with respect to what I was used to in some of my, let's say, works, like in KM theory, is that instead of fixing my attention to some invariant object which carries some flows and perturb it and look at his robustness, like we do in KM theory, well, here the leitmotif is the one of rigidity results. So one intends to characterize those systems that preserve integrability or some of its features. Okay, so of course this point of view of rigidity pops out in several domains in dynamical system and give birth to open questions and conjectures which may vary in the level of complexity depending on which notion of integrability you are looking at, whether if you intend to give a local or a global result. And just to mention a few, but of course, billiard dynamic and the Birkhoff conjectures with the rigidity of integrable billiard, where Alfonso is one of the experts here, and then also in vortex dynamics, when we look at the n-vortex problem and we wish to characterize which domains are completely integrable, or a more geometric questions of characterizing geodesic flows on Riemannian manifolds, and so on. The title was periodic tori. Why? Because, okay, periodic motions, which are supported on invariant tori, are in some sense, since again from Poincaré, okay, at the core of the fragility of integrable system, because they are somehow the most easy to break. And so in this talk, I shall speak a bit on this fragility, but also on the rigidity of this object in the frame of a symplectic twist map of the 2D dimensional annulus, where D is greater or equal than 1. So here we are talking about, so my phase space will be the, not the classical annulus in 2 dimensions, but any annulus of dimension 2D. And so I will consider what is a symplectic twist map. So I will consider C1D theomorphism of my annulus, to which is associated a lift on the universal cover F. Okay, well, if I call capital Q and capital P the images of my points, I will ask that this lift satisfy a certain periodicity in the first variable, okay, because it's the lift of my function on my TD times RD. And the twist condition, so actually the map which associate Q, P, Q and the image of my Q is a diffeomorphism of R2D, and which is a kind of non-degeneracy condition. I mean, in dimension 1, you can easily see that this twist condition consisted in deviating some vertical. Okay, so your motion is not static. And then the exactness, which means that there exists a generating function of my map F, which is called S from R to D to R, such that it is periodic. So this twist condition allows me to implement a change of variables which only looks at Q and its orbit, so the orbit of Q, so capital Q, which is periodic in my angular variable, and then which is exact, which means this way. I mean, in the standard variable QP, this exactness property is something which is stronger than the usual symplectic property, okay, which says something more than just preserving the area. And these objects, it's not something which is exotic, because in dimension 2, I mean, Moser proved that, okay, a symplectic twist map satisfying this property is nothing but a time 1 flow of a time periodic Hamiltonian, which is convex in which is C2 and convex in the fiber. Okay, so there are natural objects which can be seen as time 1 flows of some Hamiltonian. So this, I mean, my conditions, my exactness and twist conditions allow us so to, let's say, use and concentrate in focusing on my generating function, okay? And then I can recover the whole orbit just looking at it, because my p variables then are implicitly defined by the derivatives with respect to Q and capital Q of my generating function. This is pretty standard and can be seen straightforward by the twist condition. Okay, so what is the other object of the title? So the interests are Lagrangian and periodic graph. So given a continuous and Z periodic map, and given 2 integers, one m running in Zm, and the second one, which is a natural except from 0, which are relatively prime in the sense that at least one of the component of my vector m is prime with n. Okay, and let's define L to be the graph of this continuous function, then I will say that this graph is mn periodic if the nth iterate of my f of my map on the graph makes this radial transformation of Q, okay, and then falls on the graph again. So here I'm not requiring any invariance of my graph, but just that if I start on the graph, then my orbit might make n jump and then refall on the graph. while I will say that my graph is Mn completely periodic if this graph is also invariant by f. And I will, with this graph, I will refer to this graph with an Mn periodic torus, whether I am talking about its projection again on the torus, because here I was capital F, remember it is an ellipse of my map. And what does Lagrangian mean? Well, I will introduce the weaker notion of Lagrangianity in the sense that I will ask at the beginning that my continuous graph are just Lipschitz. Okay, so I will say that this graph is Lagrangian wherever, when I consider any loop and I consider the one form given by the component of my gamma of my graph, and I integrate along any loop, then this integral is 0. So since here we are in RD, this means that this one form is exact, okay? Of course, once a bit more of regularity is plugged in, then this definition of a Lagrangian graph coincides with the classical definition that you know, okay? I mean, the talk is our results are mainly two. So one concern more the fragility of periodic tori in some sense, and the other one the rigidity of the integrable map, which preserve a sufficiently large amount of such objects. Okay, and the two results are connected in the sense that the stronger one, in some sense, which is the one that I am going to present first, actually imply the second once that one takes advantage of some properties of these dynamical objects. Okay, but so given a twist symplectic diffeomorphism and given a lift, we will consider the family of symplectic twist diffeomorphisms which are generated by this family of generating function. So I take the first, okay, so SQ, capital Q is the generating function of my given f, and then I perturb it with a family of potential, okay, so epsilon is my parameter, and then G is only a C2 periodic function, okay, but okay, the fact is that here G only depends on little q, so does not involve Q and big Q. Okay, so this kind of perturbations are sometimes called perturbation in the sense of Magnet. Okay, so this is the family that I will deal with. But S here is a generating function of any twist symplectic diffeomorphism. So I'm not asked that, let's say, my starting diffeomorphism is completely integrable or have some nice property. Okay, the only property that I will ask him to satisfy is some non-degeneracy in some sense. So I will ask that f is strongly positive in the sense that, okay, if you, because of the relation that we have with capital P and the derivatives of S, once I derive with respect to capital Q, and then I derive with respect to little q, so I have a matrix, so I have this upper and lower bound, okay, and then some regularity, because I will ask that my f has the analyticity property, which is nothing but the existence of a holomorphic extension to a holomorphic diffeomorphism, which satisfy, with respect to the complex variables, the twist and the exactness property that I defined just a few minutes ago, but such that it is real on real, so when restricted to the real, so it gives me, it coincides with the lift of my given map. Just a remark here that I will come back to it later, is that for a positive twist map, so for a map which satisfies this non-degeneracy, well, any Mn periodic Lagrangian graph turns out to be in fact invariant, hence completely periodic. Okay, so remember that the difference between the two is that one is just that I fall on the graph only after n iterate, okay, while the second one, which is a stronger one, also says that my graph is invariant. Well, it turns out that strongly positivity implies that, and a bit of regularity then implies that actually these graphs are also invariant for the dynamics. Okay, so you can say the main theorem one, let's say. So if I have my symplectic twist map with my leaf and its generating function, I will consider the continuous family and the corresponding family of leaves generated by my S epsilon. Okay, if I consider this first bunch of hypotheses, so I will ask that F is strongly positive, F has the analyticity property, and not only F, but also G, which it was supposed to be only C2, admits a holomorphic extension to the complex, then, given any couple of Mn that gives birth to my rotation vector relatively prime, well, the set of epsilon such that my lift has a Lipschitz-Lagrangian Mn periodic graph, okay, so only Mn periodic, is either a whole R or consists of isolated points, okay? So here, I give any rotation number, I fix it, okay, and then I give this somehow topological characterization of the set of parameters to which correspond the map, okay, with respect to which my map has an Mn periodic graph. Well, if to A, I will add another hypothesis on my F, so 1, 2, 3 are satisfied, and in addition, my S has bounded rate in the sense that, okay, if I look at the norm as the operator norm of, okay, the second derivative with respect to Q and big Q, it's bounded, and my potential is not constant, then epsilon consists of at most finitely many points. Okay, so of course my set could be also empty, but if G is not constant, then it consists of at most finitely many points. And this condition is something that helps you to, is connected to the Lipschitz constant of my graph. So in some sense, this bounded rateness allows you to bound, okay, the regularity and the jump of your invariant graph. And so under A and B, we can get a straightforward corollary, which gives in some sense a sort of rigidity also in this first part, because under the two hypotheses of the non-degeneracy of F and this analyticity property, and then the bounded rateness, well, if the family of my diffeomorphism admit a Lipschitz-Lagrangian Mn periodic graph for infinitely many values of epsilon, then G must be necessarily constant, okay? Well, some comments on this theorem is that this result is pretty strong in the sense that, okay, we are not using at all that we are close to integrable, okay? Because it was given a map, a generical map, of course, with some non-degeneracy, but which is usual in this, I mean, in dynamics of the annulus and the circle, which is not necessarily integrable, so it's not localized close to nice system, let's say so. And then we are just fixing a single rotation vector, okay, and then getting a very strong result. Okay, while usually one also uses like the presence of some foliation and the abundance of some property with respect to a lot of rotation numbers which are held on your manifold. And on the other hand, one asks a strong assumption on the regularity of our map because, okay, we are asking of, okay, at the beginning we are just a C2 or diffeomorphism, but then we ask of the existence of a holomorphic extension. So there is this balance. And with respect to the fact that we are focusing on a periodic object, I can mention these two recent works, one by Edmond Kojinan and Vadim Kalosh in 2002, and then Kaloshin and Zhang 2018, concerning the two-dimensional billiards. So here we are in two-billiard dynamics. And the first two are focused on the coexistence of some periodic caustic in the billiard map. Okay, a caustic in the billiard, okay, correspond to an invariant curve if we look at the billiard map. Okay, so while in the second one they are more concerned always in the two billiard dynamics, but with the density of billiard of periodic constant that accumulates to some convex one. Okay, so this was the first main break. So let's go to the second one, which more deals with the rigidity of integrable system now. So here I will start by a completely integrable twist map. So I call it F0 for now. So my starting map is a map of the annulus where at the static regime, it is the Q variable, okay, is translated by this gradient of L0, which only depends on the action, okay, where L0 is a C2 at least, but C2 is enough, and then its gradient is a C1 diffeomorphism. Well, the phase space in this case is completely Fourier-ed in invariantory. Okay, so so I think that everyone in this room are used with the usual drawing of the phase space given by this kind of map. So it's gives you, so if here I have your phase space, okay, is completely foliated, okay, by these objects, which are tori, which carry a linear dynamic, okay, which is nothing but a linear flow, a translation with respect to my gradient here. Okay, so if ok, cosa? Lui? Okay. Okay, so if my lift, so given my leaf, and then if I find some P0 such that my gradient restricted to it gives me a rational vector with Mn relatively prime, then I just, with coherence with respect to the previous notation that I introduced, then my objects, okay, are the Mn completely periodic graph, okay, for my lift. In this case, the generating function, okay, is given by H0, which only depends on the difference between the capital Q and little q, and H0 is nothing but the usual Fenchel dual associated to my Lagrangian in some sense with this relation between the gradient of the one and the inverse of the other one. So in this case, oh, no, it's supposed to, okay, but everyone see this. Okay, because of this relation here, we can translate the positivity assumption that I ask on my map. And so in terms of deviation of L0, and so here we see some more coherence in the term of positivity, because here we are really asking this upper and lower bound of my Eschen as a quadratic form. Okay, so the question is taken. Okay, so the question now becomes given F0, which is now completely integrable, so that has this foliation, to which extent is possible to deform it, preserving the presence of a complete foliation of something which remains. So we will consider exact symplectic deformation of my map, my completely integrable map, and so which are given this way. So we are just composing my integrable map between Q and the action variable, which is deformed by this gradient. Okay, so in this case, the deforming family of generating function is given by this time the first part is the one corresponding to the completely integrable one. And then here I always have my potential. So G is always something which only depends on the little q variable, which translates in this gradient here. And as before, but here I remark it here, well, the hypotheses of positivity and bounded rateness are the one and come from the ones of F0, since both of the hypotheses involve the mixed derivative, okay, with respect to Q and capital Q. Well, since G here only depends on one, then it suffices that F0 satisfies those hypotheses, and then the whole family has it. And in this case too, I will ask that F0, but only F0 has this analyticity property. So I will ask that it admits an analytic extension, which is a real and real, and then I have my analytic diffeomorphism. But here I'll ask this stronger property on the regularity on the integrable, the completely integrable map. Okay, and so we have the second theorem, because if a completely integrable symplectic twist map with some lift f is given, and I call S0 its generating function, okay, and let G be my potential, which is assumed to be only C2 here, okay, and F epsilon, the continuous family, which is generated by my family of generating function, and I will ask that my completely integrable map starting point is strongly positive with bounded rate. So here I'm asking of this bound in the Lipschitz constant of my graph also, at the very beginning. And then I ask that F0 and only F0 has the analyticity property. And then I assume that there exists a rational basis Q1, QD, and the interval open such that for any rotation vector which belongs to the union of all the intersection of this rational cube in some sense, and I assume that F epsilon has a Lipschitz-Lagrangian Mn periodic graph, so only an M periodic, so I'm not assuming that something is preserved at the beginning, for infinitely many values of epsilon which accumulate to 0, and this would be a fundamental hypothesis, then G must be constant. Okay, so here, with respect to the first result, since we want to conclude, okay, this rigidity, okay, so the constant character of G, here we are using, on one hand, that sufficiently amount of Mn periodic tori are preserved. On the other hand, that of course many members of the family admits such tori, okay, and these many members must accumulate to 0 in epsilon. Okay, this hypothesis, which seem exotic, I don't know, well, is implied, for example, when we assume the existence of an open set in Rd, such that for infinitely many epsilon accumulating to 0, the map has a Lipschitz-Lagrangian Mn periodic torus for any rotation vector which correspond to the rational point of this open set. Well, this notion of the existence of many rational tori in a set like that, I think is usually also known in the literature as weakly rational integrability. Okay, so here we are not assuming of the existence of a whole continuous foliation of my phase space, but just that a rational one is preserved. Okay, and in order to see that 3 star actually meets and fill in with 3, one just choose the basis and then make sure that the straight line intersects my open set. Okay, and then one choose the interval accordingly, in some sense that, okay, so the images falls in the open set. Well, let me make some comment. Okay, in dimension 1, so why this is a strong result? Because in dimension 1, weakly rational integrability really implies the existence of a continuous foliation, okay? And one can deduce it by Birkhoff theorem and the uniqueness of existence of invariant rational circles. And so actually, if one supposes, if we were in dimension 1 and we suppose this weakly rational integrability, actually we can recover the whole foliation as the classical completely integrable case. So what it is called as a C0 integrability. Well, here, something which I insist to stress is that this theorem is not a directed corollary of theorem 1, not at all, because here, I mean, the regularity of G, which in theorem 1 was mandatory, here we're starting only with C2, okay? And so it comes only after some pages of computation and local study with respect to the Lagrangian action and some properties which are enjoined on Lagrangian and Riemann periodic torus, and of course the abundance of these periodic objects that are preserved, that one, and I will say a few words afterwards, can deduce that actually one can apply theorem 1 so that a posteriori G has much more regularity than the one that is supposed at the beginning, okay? And to mention a rigidity result but in a simpler case, let's say for the generalized standard map, I will cite this result of Bialy and McKay of 2004, where actually they proved that a generalized standard map, so I perturb a standard map, so not just a symplectic exact map, which was the general one that I considered, okay? That has no conjugate points, has to be of the trivial form Q plus P and P. But actually in their result, they strongly need the existence of a whole foliation, the rigidity result, a whole foliation of the phase space, so not just some rational family of tori, and all the compactness property that it is carried on the phase space, and it is due for the structure of the standard map. And here, I mean, conjugate points, you know, if everyone is familiar, but you have to think that two points, when you look at the tangent of your graph, 2 points are said to be conjugate, okay, when if you look at the vertical and the image of this vertical through the tangent map, okay, that there exists some iterates of my map, so let's say some n, such that afterwards the vertical is a vertical again, okay? So since, of course, this never happened, can never happen for a twist map at the very first iterate because of the twist character, but then the twist character can be missed, okay? So this is like a strong property that is also needed for the result to be whole. Well, as I was mentioning, the key step in proving this theorem is that a posteriori, thanks to the abundance of this periodic tori, then G turns out to be a trigonometric polynomial. And so theorem 1 applies. Okay, and one can deduce, plugging in some other results on the non-existence of invariant graphs that I will mention in the 5 minutes, I think, that are left. Okay. Whatever. Okay. Okay, so let me give you some ideas. Since the main ingredient to prove the rigidity property of theorem 2 is theorem 1, so let me mention the idea of the proof of theorem 1. So as I was mentioning in one of the first remarks, I just put it on the table, it was that, okay, my periodic tori, which at the beginning are just supposed to be Mn periodic and not invariant, well, one is able to prove that because of the positivity condition, which in some sense bound the rate of growth with respect to P of my orbit, the image of my point, well, one can deduce that L is actually invariant. So one use the hypothesis on the positivity that implies some superlinearity of S with respect to Q and capital Q and their distance, and the fact that actually any projecting of an orbit starting at an object like this is actually action minimizing, and then some uniqueness on the existence of this periodic Lipschitz Lagrangian graph. So one can actually deduce a posteriori that my hypothesis actually implies that my objects are in fact invariant. And then one prove at first instance a slightly lighter preliminary step, but which contains all the difficulty of the proof, in the sense that one first proof that the set of parameters epsilon, so the one with respect to which my f epsilon has an object like that, so now has an invariant object like that, has empty interior, or it is the whole R. And it is here that analyticity comes into play. So I don't know here if I will have time to detail more, but it is exactly here because one actually proved it by contradiction in supposing that if my set A contain a connected component which is not a single point, then one deduces that A must be unbounded. And so one can extend more and more and prove that it covers the whole R. Okay, and so here we strongly need the analyticity properties because one goes in the complex connected component that contains my graph, and then use the vanishing of holomorphic function to deduce this, let's say, escaping property to extend more and more. And then the game is done because then to prove the stronger one prove that once my set of epsilon has an accumulation point, okay, and because of some other topological properties, the one proved, then it also must necessarily contains a whole interval. And so because of the property that we proved at the step before, then it must be the whole R, okay. And then one actually use, okay, so now I have isolated points, okay, but I still want to deduce the constant of my potential in some sense. So it is there where I plug in, I use the Lagrangian action, which is associated to an orbit which starts on my graph, which actually turns out to be constant of a graph which is Mn periodic and invariant. And so here one does a little bit of perturbation theory and expand it, okay, with respect to epsilon. And so one starts to look at it and say, okay, since my action must be constant, then each of my terms must be constant. And because of the completely integrable character, so here, let's say, because the title must be misleading. So here, 1, 2, and 3 step, then one prove actually theorem 1. And then if one wants then to deduce theorem 2, okay, so from the first step 1, I'm plugging in the hypothesis, so the third hypothesis on the abundance of my periodic tori of theorem 2, I expand in, and because of the completely integrable character of my starting map, okay, so where given my Mn rotation vector, then the orbit, are equidistanced, okay, then I gain some telescopicity of my Lagrangian terms, and so that the first order in epsilon is something which is not completely weird, okay. So here also the special character of my perturbation in the sense of Magnier also comes into play. And so one uses the hypothesis of the abundance in order to conclude on the abundance of my tori for any rotation vector, rational rotation vector in that set, to conclude that in fact all but finitely many harmonics of my periodic potential are killed, okay? And so a posteriori G is proved to be a trigonometric polynomial, so it is analytic. And so I can plug in theorem 1 because I met also the regularity assumption on G, to deduce that in fact G is in fact, to deduce that G is also constant. And here, a key step is improving in this more general context, a more general result with respect to the one given by Mather for the standard-like map and Riemann, okay, for completely integrable perturbation of completely integrable map, but where, let's say, the completely integrable one has a very special form. It was not just a gradient of L0, but it was a quadratic form which satisfies some hypotheses. On the non-existence of Lagrangian invariant object above a certain threshold of the epsilon. Okay, so here it is crucial then that B is of bounded greatness, okay, and G, if G is not constant, then there exists a capital lambda set such that for any values of epsilon, which is farther than lambda from 0, then my map does not emit any C1 Lagrangian invariant graph. Okay, so and here the attention listener might say, okay, you started with a Lipschitz invariant graph, okay, but here I'm speaking of C1 Lagrangian invariant graph. Well, actually also much more regularity can be proved because of the twist character of the map. Because since my map are positive, then one can prove that along any action minimizing sequences, which is actually a sequences which start on a Lagrangian object, okay, there are no conjugate points. So which means that the vertical is always, is never a vertical, but once the first step is plugged in, then at any iteration it's tilted, okay? And so my map is actually always twist. And the twist characters, okay, is actually the one who helps you in gaining more and more regularity. So actually the regularity of my graph are eventually has the same regularity than my map at the beginning. So I think that I'm running out of time, and it is practically all that I want to say. And so here, since, just to finish, once that we have in this context this non-existent result, okay, then of course, if I'm assuming that my G is not constant, and then I have for a whole infinitely many values of epsilon, this family of graphs that are preserved, then I can conclude that G must be constant. Okay, so I thank you for your attention.